Good afternoon and welcome to today's Energy Seminar. To begin with, to introduce our outstanding speaker for today, I'd like to introduce Professor Yi. As you may know, he is currently the director of the Door School Sustainability Accelerator and also a faculty member in the Material Science and Engineering and Energy Science and Engineering department and a few other departments. And just to give you an idea of what a good materials research scientist he is, in 2014, he was awarded by Thomson Reuters the honor of being the #1 in the world materials science research scientist, according to their very elegant D index metric, which is focused just on material scientists. So he's kind of the material scientist. So here to introduce our speaker for today, Professor Yi.
Well, thank you, John. Great honor. Well, great honor to introduce Valerie Karplus. Today is Chinese New Year Day, first day. Yeah. Happy New Year. Yeah. Happy New Year. I'll tell you what, I invited Valerie to come, not knowing this is Chinese New Year's Day. And she happened to speak Chinese as well. And when we went to Germany together in a conference, and after talking for a while in English, she spoke to me in Chinese. I say, "What did you say?" I say, sometimes
my pronunciation.
The mind doesn't click. I said, "Did you just speak in English? I don't understand the words." And then she said, "I speak Chinese." So, well, welcome to Stanford on Chinese New Year's Day.
Thank you.
Valerie has a very exciting career. Certainly, she's an expert. I won't repeat on the decarbonization, particularly related combining engineering and policy. She did undergraduate in Yale and PhD at MIT, and later becoming MIT faculty. Later, moving to Carnegie Mellon University. Over the years, I've been follow her work, even though I don't do policy myself, but I feel it's very insightful to learn from her own work. She's not a stranger to Stanford. She was a visiting faculty back in 2017. John, I believe you were the faculty hosting Valerie. We hope to bring her back in certain capacity sometimes in the future, if possible. Valerie has won quite a number of awards. That's why I have to use my computers right here. It's just a long list of awards. Maybe I just mention one for saving time. Top 40 management professors under 40. Oh, that's really cool. They are still young.
Over 40 now.
With that, Valerie, I'll let you take a podium. Welcome to Stanford.
Thank you. Thank you so much, Yi. I have to say that it's sort of, very fortunate to have the opportunity to have a material scientist here today to introduce me as a broad-minded engineer or broad-minded economist, depending on which room I'm sitting in, to talk about these topics. I think it's so important to think about the people and the human systems alongside the technology questions. And so much of this work is actually conducted in that spirit, where we have a strong program, I think, here that's really blending together the social and economic sciences with the realities and the technology, the technical challenges that exist in material science that are related to decarbonization. And so a colleague of mine at Carnegie Mellon, Chris Pistorius, and I have sort of built a program of research over the last 5 years that really brings together two groups in two different departments. My department being engineering and public policy at Carnegie Mellon University, to develop a program of research around industrial decarbonization. And with a large and I should say significant focus on iron and steel. And part of the reason for this is that Chris is the co-director of the Center for Iron and Steelmaking Research. I'm the associate director of the Wilton E. Scott Institute for Energy Innovation. And so this was kind of a natural partnership from the beginning. And it's turned into, this is a picture of our international collaboration heading to a steel plant in Duisburg in Germany as part of the work and the program of research that I'm going to talk about today. So with that, I just want to give you a sense of why I think it's not just important to be multidisciplinary, but to take insights from deep expertise in different fields and bring them together and frame new questions and new problems. And so these are some of the areas that we're working in. We're interested in how do we plan technology while keeping infrastructure needs and uncertainties, community and workforce impacts, which I'll talk a lot about today, and then the policy, institutional, and organizational design questions in mind. And we do this together, not just at CMU, but with a number of academic collaborators, with global policy audiences in mind, as well as strong partnerships that involve ongoing collaboration and conversation with industry and partners in the community in places that are close to, in this case, where steel is made, but also more broadly in our corner of the world in Southwest Pennsylvania, where there is a lot of very active industry. And so to give you a sense of sort of how this buckets into three different sort of areas of or centers of gravity, you could say. We have research that's technical. This is the work that Chris Pistorius and I have been working on at Carnegie Mellon, where we're looking at new iron making and steel making technologies, combining performance analytics and advanced machine learning and AI techniques, along with kind of good old-fashioned experimental material science. And we're building a small furnace down in Munhall, near where we sit in Munhall, part of very just next to Pittsburgh. And then we have work that we're doing. I come with a long background in sort of economic modeling, and so we bring those modeling techniques to bear to think about process economics. We're also thinking about how do we simulate global industrial systems at a plant level and a furnace level. In fact, I won't talk about that work today, but I think that's really important for thinking about what we can do to decarbonize some of these hard-to-abate sectors. So we hope to expand that beyond that context. And then we're also very, very interested in impacts, both of technologies and policies, as well as organizational questions about organizational design, and how we look specifically in this presentation at pollution, air pollution, CO2, and then community health and workforce implications. And we do a whole lot of great outreach in the education space as well, from K through 12 through executive education and everything in between. And then on the outreach side, we have we're developing open source tools, and we're convening, in the fall, we convened a quarter of global steel production was represented in the room where we held our Accelerating Green Steel workshop to write memos thinking through what a sensible decarbonization strategy looks like. So we work closely with practitioners. We also collaborate internationally with other universities in countries where there is strong industrial production and presence. And so you think about this as sort of a coordinated portfolio of cross-disciplinary activities with funding around 10 million and a number of fantastic students, which I'll show you some of the fun things we get to do together as I go along. So the challenge: how do we close the greenhouse gas emissions gap to 2050 at a global level while delivering a full range of steel products to a growing global market? And if you, depending on which projections you believe, we have a long way to go. I mean, regardless of which projection you believe, we are today roughly stagnant in terms of total emissions from global iron and steel making. Production is also seems to be leveling off. We expect declines in China, modest declines with sort of structural change going forward. China accounts for 54% of global steel production and much of the consumption. And so we're still in a place where, I should say, steel demand is expected to rise by more than a third through 2050, or modestly, but it's not expected to fall. So how are we going to think about that? What do we need to do? Well, we're going to spend some time today looking backwards and looking forwards. And I'm going to try to do this actually relatively quickly, because I know we want to get enough time for discussion and questions, but I also have a lot to share, I think, both from the past and how we think about projections. So first of all, industrial activities are often sought after by local governments, by national governments. And you see this today in US policy for economic prosperity, for job creation, but there are also local and global environmental costs and trade-offs that we need to consider. So our framework here is going to do two things. It's going to think about the trade-off between economic costs and environmental gains and industrial transitions. In this case, we're going to look at the US steel industry and blast furnace closures. And we want to look at this at the very local level in order to inform. So our setting is going to be the transition, and I'll tell you a little bit more about the technology setting. We're going to think about this both retrospectively and prospectively. So we're trying to bring two methods together, not in the same paper, but in the same talk. And the first one is to use techniques from applied microeconomics and an econometric study, which is essentially an event study focused on the impacts locally of blast furnace closures. And then separately, we're going to use operations research methods to think prospectively about how you would transition a population of workers at one of these blast furnace, basic oxygen furnace, what I'll refer to as integrated steelmaking facilities, to a cleaner path in that same location. So we can think about our case study here will be Southwest Pennsylvania. And I think we do have operational integrated capacity, steelmaking capacity today. So this will, I think, yield important insights on its own, but can also inform how we represent these phenomena in economy-wide models that are used for climate and energy decision-making. And it also, I think, sheds importantly light on the value of in-place transitions versus geographically unconstrained transitions, which is a big source of debate. You think about climate policies leading to winners and losers, and then winners compensating losers. But we know in principle, they're the Kaldor-Hicks and sort of the standard logic around compensation is often taken for granted, but it's actually very hard to achieve in practice. So we're going to think a lot about that. This decision at the end. And I just want to acknowledge that all of this is joint work with a terrific set of colleagues. The first study with Annabelle Hu and Edson Severnini, and the second with Christoph Gillian and Chris Pistorius. So, and just to say again, we have a terrific global collaboration and NSF funding that has made this work possible. So we're going to just very briefly, so we're all on the same page. There are essentially two major routes for making steel. The first is the integrated blast furnace basic oxygen furnace route, by far the oldest. You start with iron ore. It accounts for 71% of global iron and steel production, or steel production. And the iron ore is reduced in a blast furnace to liquid iron. The liquid iron is used in a basic oxygen furnace for refining, composition, moves to then ladle metallurgy and casting, rolling, and finishing to make steel. So that route is very well established. It's also relatively high in terms of CO2 emissions, largely because of the contribution from the blast furnace iron making step. Essentially, you're structurally releasing a lot of CO2 when you combine carbon and strip off the oxygen in the reduction reaction. And so if you look at the electric arc furnace route, this is the recycled route. Traditionally, this was often called the mini mill route. You make steel from scrap in an electric arc furnace. And today, you can see that there are now sources of ore-based material that you can use in an electric arc furnace. By the way, you've always needed some ore-based metallics in your electric arc furnace. And usually that's taken the form of pig iron made in a blast furnace. So it's not perfectly clean process. There are, Ian and I were just talking about interesting ways to decarbonize the pig iron. But we can also think about direct reduced iron combining with steel scrap and using different reductants. So today, natural gas is common, but you could imagine using hydrogen. And then you start to move towards a truly net zero steelmaking process. Now, this route, by contrast, even if you include the natural gas as a reductant for iron making step, emits less CO2. And so in the US, the story is very different from the global picture. So at the global level, 70% of the iron and steel making is, again, through the integrated route. In the US, that has dropped to around 30% today. And this is how that technology evolution has happened. And what we're going to exploit the fact that there were a lot of blast furnace, basic oxygen furnace facilities that closed over the period, and furnaces were shut down between 1965 and today. The open hearth furnace, highly polluting and emitting, been largely phased out, also not cost competitive, as the electric arc furnace has increased in terms of the share of the technology mix in the US. Production from the EAF is around 70% today. And this is in sharp contrast to the global trend. You might ask, is this a decarbonization strategy the rest of the world may follow? It really then depends on the availability of inexpensive electricity, and a number of other factors. But this transition in the US was largely driven by a combination of factors, regulation, as well as the increasingly competitive economics of the electric arc furnace. So we're going to ask the question, and against this backdrop, what are the impacts of closing these blast furnaces on air pollution, employment, and infant mortality? So if you just look at the headlines at the local as well as in the national papers, there's evidence that there was a lot of local job loss. There's also a lot of evidence of environmental gain, and we would expect that. We know we're moving, blast furnaces emit sulfur dioxide. They also emit particulate matter. And what we're going to do is use a staggered difference in differences estimation technique, a econometric technique for dealing with treatment that is staggered in time. And we're going to use data from the iron and steel works of the world, which huge thanks to PhD student Annabelle Hu for transcribing this by hand. And we're going to use a number of other data sources to capture the other variables of interest. Now, because time is short, I'm going to give you the punchline now, so you can look up from your email. And the basic result here is 2 years after blast furnace shut down, we see a reduction of total suspended particulates. That's a meaningful decline in air pollution, and a bigger reduction for counties with an above median African American population share. We also see employment impacts that are very significant. So 5,000 to 6,000 jobs are actually lost with each closure in our employment data. And then we see an offsetting effect in the non-manufacturing sectors, and I'll say a little more about this. And then finally, when it comes to infant mortality, which is only part of the mortality impacts of degraded air, which as cardiovascular and impacts the lungs. You have to think about the elderly population we can't capture, but we can capture the impact on the infant mortality rate. And we find that for what we mean here by non-white is above median African-American share counties, we see that the increase in the impact on the mortality rate is significantly larger in these particular counties. So what is a blast furnace? I have hopefully made it easy for you here. On the left-hand side, those are the large furnaces. This is the Carey furnaces. This is our class gets to go there as part of our accelerating or advancing low carbon transition and industry course. It's a project-based course. And this on the right-hand side is Gary Works in Gary, Indiana. So it gives you a sense of what pollution looked like back during the period of time when these facilities were closing. And the data that we use for the study is transcribed from a book that was essentially originally published and is continually developed today by a German steel enthusiast named Uwe Niggemeier. And the panel includes 242 blast furnaces from the 1960s to the 2010s across 40 countries. Here is the US distribution of closures. You can see that many of the closures happened here in the early 80s during the collapse of the steel industry. And we're going to use a staggered difference in differences approach, which basically just focuses on estimating separately for each of the treated groups, G, the impact relative to control groups, which are considered furnaces which are in this study furnaces that have not yet closed. So we're comparing furnaces that closed to areas where furnaces closed to those that did not close. And we're going to include a full range of controls for temperature, precipitation, population, number of other furnaces on site, and other, including open hearth and basic oxygen furnaces, which are also major sources of pollution, and other operating blast furnaces. So we're looking at furnace level closures, not facilities, but furnaces. So I'll give you a sense of what we see in the data. So this is impacts on total suspended particulates with and without control variables. We see very similar pattern overall. Slightly larger but more noisy effects are estimated on the right-hand side. But you do see this reduction that begins in the year when, again, closure is announced. And then we see that once, closure occurs in year 0. So prior to closure, we do see some sort of evidence of reduction. And then we see kind of sustained reductions over time after that. So improvements in air quality locally. Employment is a slightly more complicated story. So this is overall employment in the local area relative to our benchmark year, which is 2 years prior to treatment. And then if you look, you can see you don't even really see an effect. No one would tell you this is statistically different from 0. But if you separate the manufacturing and non-manufacturing employment, you start to see a more nuanced story. So the manufacturing employment declines and then stabilizes, and non-manufacturing employment says sort of after a slow start, several years post-treatment, you start to see significant and large effects. So remember, these are local impacts of these closures. And when we look at the infant mortality figures, you see a very similar pattern as well, where you are, again, seeing a reduction that follows the trend that you see in total suspended particulates. Air pollution improvement coincides with this improvement or reduction in the infant mortality rate, or quality of improvement in health outcomes in this case. And then so what we see also, I think, is quite interesting, is that this effect is predominantly driven by counties with above median percent African American residents, and you see almost no effect in the dominantly white counties. And this is partially a story of air pollution exposure, but it's also a story of underlying health in these communities and access to healthcare and resources. And so there's both an economic driver of what you're seeing here, as well as an air pollution driver. And so that is, could be compounding an effect of air pollution if you have less access to resources. So just to again summarize, I think I've shown this visually and in the time series. You see really that the positive effects are important. I think you would look at this and say, well, what does this mean for us today? There are 14 blast furnaces of a similar vintage still operating in the United States, mostly around the Great Lakes, but also in Southwest Pennsylvania. And so we need to be thinking about those. We also know that 70% of the global steelmaking occurs through the integrated route. And so we need to think about how can this framework be applied, or how might the estimates change as you go to other settings globally. So what we're going to do now is maybe somewhat unusual, but give you a quick switch gears and talk about a prospective approach, and put that as best we can next to the retrospective approach, where we looked at localized, more localized impacts. We're going to look at localized impacts again on the labor side, but we're going to ask about what can we learn from comparing a retrospective and prospective estimate of these employment impacts using two different methods. So our econometric study found that there was a large loss of manufacturing jobs per closure. Has this changed now? Is this still relevant? Should we still be thinking about this as kind of the rule of thumb when we talk about the impacts of closures in the US? And so this study is more quickly going to ask, well, if we use a simulation approach that actually looks at people's real skills in a local labor shed and asks whether those skills of those workers who currently are employed at integrated steelmaking would match to the needs of a direct reduced iron electric arc furnace route, what would that look like? How many people would find jobs in the decarbonized version, the in-place transition? Remember that the last transition that we were focused on, the retrospective look, did not typically involve replacing the jobs with new steelmaking capacity in the same locations. Here we are thinking about relocating an electric arc furnace, and I'll show you how we've organized that. We've used actual data from electric arc furnaces on labor skills in order to understand what would be needed, and then matched those with the skills of laborers in the Southwest Pennsylvania region at a pretty granular level. So to give you a sense of where we're heading next, imagine you can think of this as what you might refer to as a steel community or an energy community of 10 counties in Southwest Pennsylvania. Pittsburgh in green, the green stars where the Mon Valley Works, or our integrated process, our remaining integrated steelmaking plant, is located. Pittsburgh used to be filled with steelmaking. This is the very last of U.S. Steel's plants that did not close in that area. And then you have some electric arc furnace steelmaking in the region as well. There are 7,000 jobs at stake across the 133 different occupations in this region, and the vast majority of them are working in production in the steel industry. And again, I'm shifting to another study, so this is joint work with Jillian, Christoph, and Chris. Our method here is going to consist of 4 stages. Also, we just found out yesterday this paper was accepted at PNAS, so I can finally say that, as I haven't been able to do that yet. So, but anyway, method consists of 4 stages. I'm going to start with step 1 is really thinking about a market-wide analysis of occupational transferability using skills, knowledge, abilities, and we're also going to include salary. Okay, so that's skills, knowledge, and abilities are terms of art that refer to specific attributes of a worker's skill set. And we're going to develop industry-specific scenarios based on technology choice. And you're going to use places that have electric arc furnace, steelmaking, and direct reduced iron production to benchmark or to develop the synthetic plant, if you will, that we would then locate where where our integrated plant would close. We're going to simulate the jobs transfer from supply to demand masses within the iron and steel industry, and then quantify outcomes in terms of workers displaced. And what we're going to ask is not whether the results match, but our first study on the labor force side, we're going to ask the question: what can we learn by putting these results side by side about what the future impacts of closures that may occur in a decarbonization transition might look like. And so we're going to use these relationships. We're going to develop a occupational skills similarity measure between any given position in the plant. So we have industrial machinery mechanics, machine setters, operators and tenders, labor and material movers, and first line supervisors. Shown here, we're gonna, the question is, how many other jobs would they be qualified for? So imagine you had a pool here of around 700 odd jobs. You're making those matches with some an index of skill level similarity, and we'd use two different indices to measure this, one based on similarity and one based on threshold. And what we're going to do is basically ask, how easily could one individual transfer into another job? And so what you're seeing here is that when graphs are dropping off more towards the right, or this curve drops off more towards the right, that indicates that the skill set is highly transferable. Whereas, by contrast, if the curve is dropping off more towards the left, you have less transferability between jobs on these three measures of skills, knowledge, and abilities. We're not considering salary yet, but we're interested in, say, for example, I'm out there hiring for my electric arc furnace facility. I might say, I need workers who have at least 75% skill similarity already, who can come in and I can train, and then they would become part of my workforce. This is giving you a sense of, it's essentially a reverse CDF, where you're basically saying how many jobs would these individuals qualify for, not just maybe it could be in a steel plant, but it could also be in a local labor market. And here we're going to look at what factors limit these transitions now. For some jobs, the limit is really on skills. So laborers in freight, stock, and material movers might lack, for example, we find there's a manual dexterity measures that are part of these SCA measures, whereas some are limited on both salary and SCAs. Others, first-line supervisors, you think about these as more of your managers, they're actually really limited on salary. You're unlikely to find a better paid position outside your current steel industry job if you're a first-line supervisor in the local labor shed, in this case in Southwest Pennsylvania. So what we're doing is combining the skill and salary data to find out where the bottlenecks are. And then we're going to ask, what is the limiting factor? And so we find different answers for different jobs. We also then look at, where are we transferring to? What kinds of jobs are in demand if we were to locate a direct reduced iron and EAF steel making plant? Remember, this is the more, or I should say, the less CO2 intensive version of the technology, where the high carbon intensity version was. You can see that for different facilities across the US, we use different electric arc furnaces with different we know how many workers are in each occupation, and we know the occupational skills, knowledge, and abilities required. So we make those matches, and what we see is that nearly everyone, or nearly every job or every occupation, I shouldn't say jobs within occupations, is filled in the decarbonized case, but there is a large number of workers who are not matched. And so that what you're seeing here in the, although nearly every job is filled, there is, so good news, because that means our labor force is potentially prepared to move into the electric arc, the readiness for electric arc furnace steelmaking is high. But at the same time, the gap between the gray bars and the blue totals around 2,000 jobs. So today, with all of the automation and modernization potentially, and certainly labor productivity has improved as a result in the steel industry, the losses look like they would be for an entire plant, including the coke works, around 2,000 jobs in this particular case of Southwest Pennsylvania. I really want to be careful not to claim to generalize, but we want to be thoughtful about whether history of past is prologue. Okay, thanks. Now, what we can also do, I think is really interesting, is to think about what about those workers who didn't match? Can they go elsewhere in the local labor market? And so we look at their and perform this occupational skills match with the full range of growing occupations in the Southwest Pennsylvania labor shed, and we find that the number of jobs available or positions that exist far outnumbers the number of workers that are displaced in most occupations, but for some, so some occupations have a large opportunity space. These are far in excess. Blue is larger than red. But if we reorder these and look at which jobs are the least likely to match, those are going to be your production and maintenance workers, your machine setters, your stock and material movers, your stationary engineers, production planning and expediting clerks, heat treating equipment setters, and industrial machinery mechanists. These are the jobs that are most at risk. And what does this information help us do? It helps us plan for a local transition. This is not a sort of, you might say this is a helpful methodology in a lot of places, but the results from this study will not be one size fits all. They'll help us understand where we might focus public resources usefully in a particular area in face of a particular local transition. Let's see. Yeah, so most of these at-risk jobs are generally production related. And so just to sort of conclude on this study, key points here are that our integrated steelworkers are well equipped to transition to the DRI and EAF occupations, but there's still great heterogeneity among these limiting factors. And managerial workers are in a much better situation than your production workers. The decarbonized pathways also require substantially fewer employees. And when we were working on this, the Tata announcement that they were going to transition their integrated steelmaking to an EAF included very similar numbers to what we had found with the Southwest Pennsylvania case. You only need 15 to 30% of your initial worker supply mass to run these decarbonized facilities. So this could potentially result in significant unemployment. And that unemployment burden seems to fall predominantly on the production workers who have the least amount of job transferability at the outset. However, we can think about this as a policy opportunity for planning and targeting retraining and upskilling, wage insurance policies, and other specific investment and development opportunities. And so I think this just brings me to leave you all with a question. So you'll get to ask me lots of questions, so I'll put a few out there myself. What can we kind of learn about the value of allowing market forces to run their course and determine the geography of production, versus to what extent should we really consider the decarbonize in place option, where, as in the Southwest Pennsylvania simulation, you replace the integrated capacity with the lower emitting DRI EAF capacity. And I think you can start to compare on different dimensions, right? So there are some trade-offs in the economics. The market forces would presumably reflect least cost conditions. The rise of the electric arc furnace was highly driven by sort of the improving competitive advantage of the very nimble electric arc furnace producers like Nucor and Steel Dynamics. They also located in states where they were not, they were essentially right-to-work states, not union states, and so may have faced fewer constraints. CO2 emissions, you're getting the same reduction at the global level. In terms of health, I think it's a really interesting question what decarbonization options mean when you transition in place for local community health and air quality, depending on the reductant you use, depending on the configuration. If you retrofit existing integrated facilities with carbon capture and sequestration, turns out in other work we find that the net benefits go up by a factor of 10 if you include the top gas pretreatment before it enters the capture inlet. So that means that you're basically taking out a lot of the local pollutants at the same time, and you're protecting your downstream pipelines, the integrity of your downstream pipelines by removing those potential corrosive elements. At the same time, you're essentially improving the local air quality impacts of that technology. And then finally, in terms of jobs, I think we can say, based on this, comparing these two studies, that the local labor impacts may be more modest than a single blast furnace eliminating on the order of 5,000 jobs. But decarbonization in place, while it may reduce jobs, it still might allow for some significant fraction of the labor force to continue working. And we also need to think very hard about interventions to help those workers that are displaced. And so we can sort of ask this normative question. This is not one that we'll solve today, but how do you think about these trade-offs, both at the local level and at, all the way up to the global level, although national governments grapple with these questions a lot. And then for the, for policy, how do we design training programs and support programs that help specific occupations and workers in those occupations move to other jobs in ways that pave the new paths to local economic prosperity and help us address some of the, and there are many other barriers that persist in these situations, and other work that we're doing is really focused on trying to more deeply understand those. But this challenge, I think, is an important and contemporary one. If we can get it right, then I think we'll have a smoother path to deep decarbonization. Thank you.
Any questions, students? First, as usual. Any takers? Questions, comments, suggestions?
Yes.
We shouldn't use the. We have this room has a fancy acoustic.
Okay, I'll speak up,
but the system should be able to handle the transfer of the.
Yeah, thank you for your presentation. I guess I was interested in if you could talk more about like the role of monetizing damages from air quality, poor air quality.
Yeah.
Just in terms of like when at whatever level you're looking at making sort of like accounting for the maybe like loss of jobs, but better air quality, but being replaced with lower paying jobs. I guess, could you talk more about how that comes into sort of a decision making?
Yeah, so I think it's very challenging, or at least there aren't that many studies in economics that try to monetize the value of job loss. Specifically, they're interested in broader welfare measures. So, and job loss would be kind of, you might think that it moves in the same direction as those aggregate welfare measures, but it doesn't tell you about jobs, which is why it's nice that you can use these same econometric techniques to look at outcomes in their natural units. So I'm a big fan of always looking at the outcomes in their natural units and then monetizing them appropriately and in accordance with often a requirement of policy or a process, decision-making process. So we think about benefit cost analysis is all about monetizing some of these impacts. Right now, I think we do a fairly good job of monetizing, relatively speaking, the economic. Well, we have a way of monetizing the health damages from air pollution, and that's through the value of the statistical life. So what you're doing there is you're basically saying that we have various estimates of premature mortality. Those today in our prospective analysis would include both the elderly as well as for the full spectrum of the population. Simulation models like the AP4 model and others that give us that information. And you can start with that and say, okay, what do if you take sort of the accepted values of a statistical life, the EPA, you're in sort of the 10, 13 million per life ballpark. Comes from labor market data. It's not the value of life, it's the value of a statistical life. You can do that. And if you do that, you will find out that it is the amount of benefit that you generate from the improved air quality roughly corresponds to the bill you would pay to decarbonize these facilities, considering that many of these facilities are going to have a residual amount of air pollution coming from them, but that delta is so huge that it would pay for decarbonization. So it is important to monetize, and it's important to think about the implications of monetizing, but not to lose sight of the natural units. So I think that that's a direction we're going in, sort of with a prospective study on air quality that kind of accompanies the jobs picture. Thanks.
Thank you for the talk. Maybe to build on this, the numbers that I get from the talk is 11 to 14% reduction, right, in total suspended particulate. How localized?
14 micrograms per cubic meter. So, yeah, actually, I can go back to that just a second.
How localized is that around how many people does that affect? Because it's a very significant impact, right?
Right, and those in the models, the integrated assessment models that will help you understand that the relationship with the monetized damage, health outcomes and monetized damages would be more comprehensive. But what we've done here is really looked at within a 30-mile radius of the plant. So let me see if I've got the right one here. Yeah, so it's about I am 9% reduction.
Over in the foreside.
Yes.
Yes. Do you have any data on how the old technology what labor reduction there would be if you don't change the basic process, you just use modern methods of production? Because my sense is that across all industries, there's been a reduction in employment per unit of output.
That's true.
And what fraction of the effect you're seeing here, job loss, is just due to technology improvement and not specific to the process?
So I've netted that out through the staggered difference in differences method. And the assumption is that a plant that did not close in that particular year was also facing all of those downward pressures or and increasing its own labor productivity in ways that are would account for that trend in the baseline. So what you're seeing is the delta between the plant that closed and the plant that didn't.
But just to push back, those are incremental improvements that can be made to an existing capital plant, right? That would cause that steady reduction in employment in the existing plant. I'm thinking.
Right, but I'm localizing that's why I need to control for that. And that's how the econometric method, it allows us to think about, there's a parallel trend. It's probably for labor productivity improvement, it's going to translate into sort of two downward trends in employment, and now one plant closes. But this one's still going down. So I'm always comparing to that one that is on that same track in terms of.
I guess the extreme case would be a brand new plant opened in a country that didn't have cheap electricity or highly available scrap, et cetera. Would they have a notably lower employment per unit production?
You're getting at a question I think it's great. When we go to the Mon Valley Works, which is our integrated steel plant locally, they look at us and say, if you built this plant again today, you would use 4 crane moves. Today we use 21 because that was 100 years ago. And so I think you would absolutely, brand new plant would be built differently. But these plants weren't undertaking that degree of retrofit. They were simply closing blast furnaces on site. We went through that. It's a fascinating compendium of the history of the blast furnace in the data that gives you a sense of which other assets on a site closed at the same time. And we don't see that kind of major capital retrofit happening contemporaneously.
Other questions at this point? Seeing none, I have one. So could you give us a little bit of teaser on your kind of supply chain international machine learning work?
Sure, yeah, absolutely. So
much more technical study, but could you give a high level summary of what you're finding there?
Yes. So what we're doing is, first of all, just trying to recreate the global fleet of furnaces in operation today using a machine learning technique, which essentially allows us to take cost models that are available from an industry source for about a third of the global steel making facilities and use machine learning methods on observables that are available for the full 300 odd sites. This is in the case of blast furnaces, it's more for all the furnaces. But within each technology category, we are basically training the models on the sort of detailed cost model, the richer data, and then we test it within the sample where the data are available, and then we are able to say, okay, these performance is good enough that we feel actually comfortable using the machine learning algorithm to interpolate the full set of plant level data for each technology. So we could look at blast furnace operations across the, if you wanted to get your total addressable market for, say, biochar technology to bring down blast furnace emissions or hydrogen injection for that matter, the whole idea is to be able to estimate this with a essentially a framework that allows you to generate this plausible synthetic data, and then look at, of course, it assumes that you're always comparing to an existing plant's economics, and so you can constrain the model or maybe unconstrain the model in different ways to allow it to locate steel production in other places. But we're hoping to kind of build this up into a more generalized modeling framework.
Give E the last word here. The big rigs are fighting it out here.
So Valerie, since you have so much knowledge about steel, I want to ask you, given the new administration in DC, tariff is building up, who knows what would happen. And once the tariff, let's say for steel, gets to a certain level, so I'm trying to see, what's to build out significantly new steel making plan. When the tariff gets to what percentage, this sounds like, there will be in terms
well,
of US steel pool.
CapEx is a formidable obstacle. So yeah. I think at the point where maybe you take those tariff revenues and you use them to fund modernized steel plants, you might start to see new steel plants, and you'd want to do that obviously with a certain degree of attention to, the discipline and the way those investments get made and so forth. But I do think there's not a single level of tariff that would trigger. Trigger a major investment. I think it's much more a question of sort of company culture and mindset around investment planning. And so you might see, you could imagine there are companies globally that have longer or think about these investment decisions differently, longer horizons and so forth. And so it's an open question, really, especially given the small. U.S. is only 4% of global steel production. I think our biggest opportunity is in the indirects, the moving into steel that's used in other products that could be made here rather than imported from somewhere else.
Great. So,
okay, quick question. You said you looked at salaries too, in addition to numbers of jobs, and yeah. So could you say a little bit about salaries in that? Yeah. Scenario that you evaluated?
So it turns out that in union states like Pennsylvania, steel workers are paid well above median wage for the area and have very generous benefits packages. And we are using salary data that includes an estimate of what those benefits packages look like. The transition is actually harder on salary for managerial positions because they're at the sort of top of the ranks locally in terms of how they're paid. The production workers, it's really the skills that are holding back the transitions. And so I think you could imagine local stimulus policies that might bring employers, like we're seeing kind of a mini tech and AI boom in Pittsburgh. That those you could imagine, you could ask whether a steel executive could transition to a venture-backed startup, but I've seen it happen at least once.
Great. That said, I'd like to thank Professor Karplus for sharing your insights on this very, very hard to decarbonize industry with us.
Thank you.
Thanks to the audience for great questions.
Thank you.